Now that we've covered measures of location and dispersion, let's talk about which ones apply to which types of data, to which levels of measurement. Out of all the measures of location and dispersion that we covered, only one of them applies to nominal data, and that's the mode, which, as a reminder, means the value that shows up the most. So it makes perfect sense to say that brown eyes was the most frequent eye color. With nominal data, we can also report frequencies, like saying 5 people had brown eyes, 4 had green eyes, 3 had blue eyes. Or we can report proportions or percentages, which are also called relative frequencies. They're just the frequencies divided by the total number of observations. So you can say 40% had brown eyes and so forth. But since nominal data has no ordering, we can't do median or anything like that. We also can't calculate a sum. You can't add green eyes plus blue eyes. That doesn't make any sense. And don't confuse a sum with adding the frequencies. Of course we can add up all the frequencies, how many people had blue eyes and so forth. But the total would just be the population or sample size n. It wouldn't be a sum of the actual values of the data, which only makes sense with numerical values. And since there's no sum, you also can't calculate a mean, because the mean is a sum divided by n. You also can't calculate variance or standard deviation, because for one thing they depend on mean. Now when we move up to ordinal data, we still can't calculate a sum or a mean or standard deviation, but we can use the median. Why? Because ordinal data has a meaningful order. So we can rank values and find the middle one, even if the gaps between ranks aren't equal. With interval data, things change. Here we can do sums, calculate the mean, variance, and standard deviation, because the numbers are on a scale with equal intervals. But one thing we cannot use is coefficient of variation, or CV, because that's a ratio measure. And interval data doesn't have a true 0 point, which is needed for ratios to make sense. Finally, ratio data has equal intervals and a true 0 point, so you can use all the measures. Here's a table with an overview. Finally, we get the measures of shape. There are others, but we will only focus on skewness, which is simply how symmetrical the data are. In this backs and whisker plot, we can clearly see that the left whisker, as well as the left side of the backs, are shorter than the right whisker and the right side of the backs. This data is positive skewed or right skewed, which means that the data is more spread out at the higher values and more concentrated at the lower values. If it's the other way around, it's called left skewed or negative skewed. And if it's not skewed to either side, it's called symmetric. For symmetric data, the median is centered in the backs, and the lengths of the whiskers are equal. Also, for symmetric data, the median is equal to the mean, because the left and right sides of the data are mirror images. For every value below the center, there's a corresponding value equally far above it. So the mean will end up being the median. Also, if there's only one mode in symmetrical data, it has to be right in the center. Otherwise, it wouldn't be symmetrical. So the mode is also equal to the median and the mean. For positively skewed data, there are some large values pulling the mean to the right. So the mean is greater than the median. Now for negatively skewed data, there's some small values putting the mean to the left. So the mean is less than the median. Okay, so we're done with measures of location, dispersion, and shape. We'll now cover frequency distributions, histograms, and density plots, which are important tools in descriptive statistics for organizing, summarizing, and presenting data. A frequency distribution shows how often each value or range of values occurs, helping us understand the shape and spread of the data set. For example, here's the raw ordered data representing the ages of 32 students in a class. To get a better picture of the data, we can count up how many times each value appears and construct a frequency distribution like this. The sum of all the frequencies adds up to the population size. Looking at this table, we can see that 21 is the mode, 20 has the next highest frequency, and so forth. But with so many values, this table is very cluttered. To simplify things, we can group the data into equal size intervals and build a frequency distribution based on those groups instead of listing every value. The choice of interval size is flexible. In this example, we use 3-year intervals. When we group the data, we lose some detail, but the result is a cleaner, more readable summary. For example, it becomes immediately clear that the majority of students are between 21 and 23 years old. The total frequency across these grouped intervals adds up to the full population size, just like in the ungrouped frequency distribution. So far we've been dealing with discrete data. For continuous data, there are two key differences. First of all, you must group the data. If you list every individual value, the frequencies for basically every single value will all be equal to 1, because every data point has a different value. Second of all, for continuous data, the range of values in each interval goes up all the way to the next interval. For example, in our discrete data set of students' ages, we chose an interval size of 3. So the age ranges go from 18 to 20, 21 to 23, and 24 to 26. But for continuous data, intervals of the size 3 go from 18 to any value under 21, then 21 to any value under 24, and so forth. In reality, we always limit the number of decimal places we use for continuous data, so all data is technically discrete. But because in theory we could always choose to work with more decimal places, we still treat it as continuous. This is obvious, but just to make sure it's clear, the frequency values themselves, which are just the number of data points within a certain range, are always discrete whole numbers, even for continuous data. Instead of using a table, we can show the same frequency distribution in a bar graph called a histogram. Each bar represents a bin, which in histogram terminology just means a group from the equal intervals the data was grouped into. And the interval size is called the bin size. The height of each bar or bin, or basically the y-axis, shows the frequency, or how many students fall into each bin. This histogram that has gaps between the bars and gives you the age range under each bin is only appropriate for discrete data. And this type of histogram is technically the correct way to make a histogram for discrete data, which don't cover any actual continuous interval on the x-axis, only discrete points. So the histogram doesn't show an x-axis. The width of each bar in such a histogram doesn't matter. It doesn't represent anything. But usually you'll see histograms like this, which have a real x-axis that shows, in our case, the age of the students. The width of each bar reflects the bin size, which in our case is 3. 18, 19, 20, 21, 22, 23, 24, 25, 26. And again, the y-axis shows the frequency. This is the correct way to make a histogram for continuous data, which covers all the values on the x-axis continuously. But it's often also used for discrete data. For discrete data, each bar only covers 3 values at 3 points: 18, 19, 20, then 21, 22, 23, and finally 24, 25, 26. That's why this type of histogram that covers the entire continuous interval on the x-axis is not technically correct for discrete data. But to make sense of it, you just have to interpret each bar as representing only specific discrete values, not the entire continuous interval it appears to cover on the x-axis. Sometimes it's more useful to look at the proportion or relative frequency rather than the absolute frequency. We get the proportion by dividing the absolute frequency by the total number of data points n, uppercase, lowercase, depending on whether it's a population or a sample. In our case, n is the total number of students, which is 32. So we divide each value by 32 to get the relative frequency. 10 over 32 is 0.3125, 17 over 32 is 0.53125, and 5 over 32 is 0.15625. If we sum up the total frequency, as we said, we get the population as n. But if we sum up the relative frequencies, we always get 1, because the sum of all the proportions is always equal to 1, or 100%. Or another way to think about it is that these values add up to 32. So if you divide them by 32, you get 32 over 32, which is 1. And here's a histogram for relative frequency. It's the same as a histogram for absolute frequency, but the values on the y-axis were divided by 32. And the tick marks were adjusted to show simple decimal increments 0.1, 0.2, and so on, rather than the irregular decimals resulting from dividing by 32. If you didn't know what n is, you could get n from the original histogram that shows the absolute frequency. Let's go back to the original histogram. So we have 10 plus 17 plus 5 equals 32. Here's a histogram showing the distribution of how much time employees spent in the office on some particular day. What is the bin size? It's the width of the bars, which is 2 hours each. Time is a continuous variable, so the first bin covers all infinite values from 0 to 2. In other words, 6 employees, right? It's right between 4 and 8, so that's 6. So 6 employees were in the office for an amount of time somewhere within the infinite values that are between 0 and 2 hours. How do you get the relative frequency for this histogram? You divide these values in the y-axis by the population size n, the total number of employees. How do you know what n is? It's the sum of the total frequency. So you count the heights of each bin, 6 plus 6 plus 16 plus 20 plus 10, right? It's between 8 and 12, plus 4 equals 62. Total number of employees is 62. So to get the relative frequency, divide all these values on the y-axis by 62. For example, 20 over 62 is 0.3226. So 32.26% of employees spent between 6 and 8 hours in the office. If you want to convert this histogram to relative frequency, you would divide all these values by 62, but you wouldn't just write these values like 0.3226 in the y-axis. You would adjust the tick marks to something like this. So this height is still 0.3226, but the values on the y-axis are 0.05, 0.1, all the way up to 0.35. You've likely seen data represented by a graph with a smooth curve like this, called a density plot. How does it work? Imagine you have a very large data set, and you make a very fine histogram with thousands of such narrow bins that you can no longer make out individual bins. It just blends into a smooth curve. That's essentially what a density plot is. But how do you read it? It doesn't have any individual bins. You might say, what's the problem? Just imagine that there's a very narrow bar at every point, and the value on the y-axis tells you the relative frequency at that point. So in this density plot, according to your argument, the relative frequency of men with a height of 170.00 centimeters is this value here, which is a little under 0.05 or 5%. And then the relative frequency of 170.01 centimeters is this value here, which is again a little under 5%, but a tiny bit more, and so forth. But this makes no sense. For one thing, the total relative frequency has to add up to 100%. If you keep adding 4 or 5% at every point in this area, you'll get way over 100%. You'll actually reach infinity, because at any interval, there are infinite points. So what is the relative frequency for an individual point? The relative frequency for an individual point is 0, because the more precise you get by adding more decimal places, you'll eventually reach a level of precision where no one in the population has that exact value. So how do you read a density plot where the values on the curve keep changing at every point? The answer is that to read a density plot, you have to pick some interval, any interval you want, and the relative frequency, or the proportion of the data that's in that interval, is equal to the proportion of this lavender area, the area under the curve, that's in that interval. Let's say this area is a third of the total area, then we know that a third of the population has a height of between 150 and 170 centimeters. Or in other words, the relative frequency for the interval 150 to 170 is equal to a third, or 33%, assuming that this area is actually a third of the total area. But when we talk about an area under the curve, instead of saying that it's, let's say, a third of the total area, we just say it's equal to a third, period. We just define the total area under the entire curve to be equal to 1. And now half of the total area is equal to a half, a third of the total area is equal to a third, 0.007 of the total area is equal to 0.007, and so on. So we just say that the relative frequency for an interval is equal to the area under the curve for that interval. Let's say this area here is equal to the relative frequency of this interval. This area here is equal to the relative frequency for this interval. It doesn't matter how big or small the interval is, it will always be equal to the value of the area under the curve in that interval. But how do you figure out the area under the curve for an interval you're interested in? Area is width times height. So if you multiply each value on the y-axis, which is called the density, by each tiny width over the interval you're interested in, you get the area under the curve in that interval. Okay, so what is the area under the curve for, say, the interval between 170 and 180? The width here is 180 minus 170 equals 10. The height in this interval is roughly on average 0.053. So the area is equal to 10 times 0.053 equals 0.53, or 53%, which means that a little more than half of the population of adult males is between 170 and 180 centimeters tall. What about this interval between 190 and 195? Density here is on average 0.003, and the width between 190 and 195 is 5. So the area on the curve is 5 times 0.003 equals 0.015. So the proportion of the population that's between 190 and 195 centimeters tall is around 1.5%. So to be clear, the density, the height of the curve, doesn't have any meaning in and of itself. The density only gets meaning when you multiply it by the width of some interval on the x-axis to get the area under the curve. That area is equal to the proportion of the data that falls in that interval. Obviously, density plots are only for continuous data. Discrete data can't form a smooth curve. Earlier we saw how a box and whisker plot shows the skewness of the data. You can also see the same thing from a density plot. Symmetric data produces a symmetric density plot. Positive right skew data shows a tail to the right. And negative or left skew data has a tail to the left. Density plots tend to show nice smooth curves like you see in these examples. Why don't they look more random and chaotic? Because the values we observe in datasets are not random in a chaotic sense. Whatever the variable is, whether it's heights of buildings, students' scores, incomes, whatever it is, it usually follows some mathematical structure that underlies the behavior of this phenomenon. For continuous data, this structure is called a probability density function, or PDF, which when you graph this function, you get a density plot like the one shown here. A PDF is a mathematical formula that describes the probability distribution of the data, which means how likely each value is to occur for that particular phenomenon. Not in terms of individual values, because for continuous data, the probability of any individual value to occur is 0, but in terms of tiny intervals on the number line. The reason density plots of observed data look like probability density plots is because for a large enough data set, the distribution of values will closely match the shape of the PDF that underlies that particular phenomenon. The larger the data set, the closer and closer the distribution gets to the theoretical probability distribution based on the PDF. So for large data sets, relative frequency or proportions of observed data and probability are two sides of the same coin. There's more to talk about PDFs and why proportions and probability are two sides of the same coin. But first, let's take a step back and learn about the basics of probability, which will begin in the next lecture.